Buotte, and Holly's a postdoctoral fellow at the University of Idaho, and I'll just let her carry on.
Thanks. I appreciate the invitation to come and talk a little bit about some work I did recently, and I hope that it just gives a different way of thinking about the work you're already doing. So I did work on looking at mountain pine beetle outbreaks in whitebark pine and what are the climate influences on the recent outbreaks. And thank our funders, of course. So 2 objectives. One, I think I will take this off. Just to understand, things get a little clipped off. To understand the climate influences on the recent outbreaks in whitebark pine. And the recent outbreaks were a lot different than in the past. They're much more extensive and more severe. And then second, can we estimate the historical and future climate suitability for whitebark mortality from beetles? And I will echo Bob's dissatisfaction when trying to predict the future. There's unknowns all over the place. But I think we can say something. So I'd just like to start at just a short introduction or summary of the mountain pine beetle life cycle. So the adults attack trees and lay their eggs in the tree, and that happens in the late summer. And then those eggs develop into larvae, and then they overwinter under the tree bark. Their development stops during the winter, and then when it warms again in the spring, development resumes. Then they emerge from the trees the following year, and that's when the trees turn red. So a red tree was killed the year before, and the adults fly and attack new trees. And this is really a very climate-driven life cycle. So for all of this to happen in 1 year, and for adults to all emerge in late August, and to have a mass attack is what the entomologists call adaptive seasonality, and it is strictly controlled by temperature. The trees, however, are not passive. They try and defend themselves by producing pitch to literally pitch the beetles out of the tree. And a tree can only do that if it's healthy. If it's a drought-stressed tree, then those defenses are much reduced. So precipitation and rainfall and snowfall also has a large influence on beetle attack success. Then finally, in the winter, when development stops, beetles cold harden themselves like many insects do, and they can survive some really severe cold temperatures, but if it gets cold enough, about -30 C, that will kill beetles. And if any that are laid later in the fall that haven't had the time to produce the cold hardiness, if temperatures get low or in the late fall, that can kill beetles. So winter mortality, that's another important place where the climate has an influence on a successful outbreak. So we developed a statistical model informed by the processes that we know influence beetle life cycles and the probability of a successful attack. And so we included, you need to know how many beetles were there before, because the more there are, the easier it is for them to swamp tree defenses. We needed to know what the stand structure was like, and then we needed to have climate metrics that represented the adaptive seasonality, the 1-year life cycle, winter mortality, and the abilities of trees to defend themselves. So I just want to give a little bit of how we did this, because I know modeling is often a black box, and if you don't see some of what goes into it, it's hard to know whether you believe it or not. So I just want to give a little bit of what's in this model. The response is whether or not there were whitebark pine in a 1-kilometer grid cell, and that comes from the Aerial Detection Survey, Forest Service, which are, Bob, you fixing that? Thank you. That's from the U.S. Forest Service flights, which I'm sure many of you are familiar with, a pilot and an observer recording where they see mortality, the tree species, and what they think the damaged mortality agent was. We also used that data to create a variable of the area of mortality in the previous year in that 1 kilometer cell, so in that stand, and then surrounding, so we could account for beetles coming in from other places. And that was not just whitebark, but lodgepole. So if you're on the edge of a lodgepole stand that had a big mortality event last year, those beetles are available to attack whitebark the following year. Then we wanted to try and estimate how much whitebark pine is remaining, what has been killed and what is left to be killed. Because if there's nothing left to be killed, you're not going to see any mortality. So we did this with using the aerial detection survey and subtracting, assuming that a kilometer cell was, that it is 100 hectares, and that represented the available area of whitebark pine, and then subtracting the mortality from the beginning of the outbreak. We also used stand age from a Westwide map, and then we tried to use some better measurements of stand structure, but we were doing this across the range of whitebark in the US. And those data just don't exist at that spatial extent, so we couldn't. Then we used a bunch of different climate metrics to inform the model that we're representing adaptive seasonality, winter mortality, and tree defenses. And because beetles could have a 2-year life cycle in cold environments, we used those variables for the current year plus 2 years to represent that. And I'm not going to go through what all of those were. And so all the models had these representations of beetle pressure, stand structure, and the climate variables that I described, representing those processes. And then we used a model selection process to determine the model that fit the data the best. And this was, again, across the range of whitebark pine in the western US. So these are the variables that we retained. And adaptive seasonality, we had 2 temperatures, the average fall temperature and then the average spring and summer. Beetle winter mortality was best represented by the winter minimum temperature, and tree drought stress by summer precipitation from the year of attack and the previous year combined. And this is what the model looks like across, again, the western US. It did, pretty well matching, didn't catch all of the bumps and increases and declines, but felt like it did pretty well, and this is looking at it as against the observed, against predicted. So we felt like we can actually use this now to say something about what are the climate influences. So this is what happens as winter. These are log odds plots from because the model is a logistic regression model. So winter temperature is increasing. That means beetle survival is increasing. That means tree mortality, the chance of tree mortality is increasing. Conversely, in really cold winters, more beetles die, and therefore the tree has a better chance of surviving. And similarly, similar plot structure for looking at, do beetles have a 1-year life cycle, and do they all emerge at the same time? Fall temperature was really the most important. And this, as fall temperatures, when they're warmer, that allows the beetle eggs that were laid later in the season to catch up. And so all the beetles enter winter at the same ideal stage of cold hardiness, and they all survive, and they all fly the next year and attack trees and kill them. And, keep doing that. Given the data we had, we really can't say that there is much of an effect of April through August temperature. Then tree defenses represented by summer precipitation. When there's less precipitation, trees have lower defenses, and so there's a greater chance that they will die from beetle attack. This all makes sense based on work we did solely in the Greater Yellowstone to start this project, and based on what we know about beetle outbreaks in lodgepole pine, which is their more common host. So then we wanted to take this model and apply it to historical data and to future climate data. The model was developed on data from 1997 through 2009. So we wanted to go backwards and forwards in time. And when we applied the model, we then calculated what we call a climate suitability index. So this is the model, and again, I just want to show a few of the details because I think it helps to think about it. These are the log odds of a tree dying. This is beetle pressure and stand structure, and these are really often not known in the past, and they're certainly not known in the future. So we can't predict the probability of a tree dying because we don't know those things. We could make them up, or we could just use what we do know, which is the historical and future climate data, and from that calculate a climate suitability index as the sum of these terms. So that's what we did. And this now is just focused on the crown. This isn't west-wide anymore. This is just looking at beetle outbreaks of the weather suitability, climate suitability in the crown ecosystem. And the blue line is the effect of winter temperature on the probability, or on the log odds of trees dying. And so when it's high, there's a better chance of trees dying. When it's low, there's less chance. And what to me is the most obvious trend or pattern in this is that in the past, there were a lot of cold winters that really limited the beetle population. But once the outbreak started, there weren't any. So this historical limitation of really cold temperatures just quit. It didn't happen. And this is true in the greater Yellowstone, which is where I live, as well as in the Crown. It's not true in the Cascades, which is another story. And so then we wanted to, also there are some peaks of drought. This is it's high suitability for mortality, so it's drought. There's not very much precipitation happening. And those really seem to occur, I mean, it's not a consistent relationship, but that does seem to be influencing and contributing to the beetle outbreaks. Again, that's consistent in the greater Yellowstone and the Cascades. So then we want to look to the future. And so we chose to use 10 different global climate models, and all forced with one that the dire, we do nothing about greenhouse gases, and we keep emitting, we keep increase our emissions. The RCP 8.5, we forced it with that since that's where we're headed. And the range then is shown in this gray. So some models, have different projections and they yield different answers, but that bounds the range of these 10 that do well for historical climate in the Intermountain West. And the dots are the average of those 10 models. And this line is what the average climate suitability index was from 1950 through 2009 for the Crown. And this is looking at winter temperature. And you can see, again, a lot of years with really low suitability, and then there just aren't any. So what it's saying is that, this recent outbreak seemed very strongly driven by a lack of cold winters, and we're not going to get more. There's going to be fewer and fewer cold winters into the future. And these are just looking at the other parts of the model. This is the fall temperature, the summer precipitation. And then if you put those all together, there's not much change in the average, but again, there is a reduction in the really low suitability years. But again, the uncertainty, it's not just uncertainty in the climate data, it's uncertainty in the modeling that we did to estimate these relationships. And it's out here in these years where the temperatures are in the ranges that we don't have much to go on right now. I did limit these data to, I chopped them off at what was the maximum observed temperature now. So we're not projecting beyond known conditions, but we are projecting at the very limit of what we can really say something about. So there's a lot of uncertainty when we get out here in There's uncertainty in what the climate will do, and there's uncertainty in the ecological responses to that uncertain climate. So, of course, modeling has lots of caveats, and I'll just mention a few of ours. One is this, we couldn't account for the mortality that happened before 1997. And of course, in the Crown, the majority of mortality probably has happened before 1997. But I will say we have better historical data for the greater Yellowstone region, and we were able to look at, well, what if we said, we're assuming this is all available to be killed, but what if we said some of it can't, and it didn't change the climate influences. So it wouldn't change our interpretation of what the future climate effects would be. And the second is stand structure. And this is obviously not whitebark, it's lodgepole, but that makes a difference. And beetles do only attack the larger diameter trees. And so if we don't have a good estimate of how many suitable trees are there, that makes it harder to estimate then what will die and what won't. Still, though, when we did remove the stand age from the model, which was a really strong predictor, it didn't change any of the climate. So we still feel pretty confident that the climate relationships are pretty robust to what else is in the model or not in the model. So what does it mean then? How does our little bit inform how might whitebark persist in a warming climate? And to me, I think it means that it's going to be this dance between the time to cone-bearing age and the interval between cold winters. And as long as we get a couple cold winters that kill off a lot of beetles, then those trees have a good chance of surviving, and beetles, not blister us, not included in this, but that's what we need in the near term. Then how can this inform what people are already doing and thinking about in terms of management? And I think about it as a risk management portfolio, because we don't know very much, really, in the greater scheme of things. And so I think there are a couple things we could do. One is to focus on sites that are likely to experience cold winters. And that can be from simply an elevational, or you know that there are places that have cold air drainage that it's just cold. And so for any particular location, that's not something that a global climate model will ever be able to pick up. But it's something that we know because we've been on the ground. And so I think that's an important consideration for keeping beetles out. And then second, maybe we do want to think about low elevation sites that might experience warming, because it looks like as fall temperatures warm, that's going to kick the beetles out of that good temperature regime that allows for a one-year cycle. So maybe we do want to do some management at these lower elevation places that maybe don't look so good now because they've been pretty decimated, but maybe in the future that will actually be a fairly suitable place. And all of this, as Bob said and as Diana has said, we want to foster landscape heterogeneity. And these are just a couple specific ways in thinking about beetle effects that I think we can do that. And we want to foster genetic diversity. So, a mix of genes and placement on the landscape. And I think can either be an optimist and keep on going, or you can be a pessimist and quit. But so I'll choose to be an optimist and keep on going, and I think there really is quite a lot we can do. Thanks very much.